Hey, thanks for joining us. So my name is Jennings. I'm a product manager for BigQuery. And today we're going to spend a little bit of our time talking about geospatial analysis in BigQuery and how our customer, Geotab, has been using that to supply their customer, i.e. municipalities, with interesting insights and data. I don't know, how many people here went to the Spotlight session for BigQuery a little while ago? OK, a few. So you guys know a secret that not everybody knows, and so keep it to yourself for a second, because I get to reveal it. So we have one feature here to launch that I'm really, really excited about. So let's go ahead and get right to it. All right, so there are three of us. So I'm joined today by two colleagues from Geotab, which is a BigQuery customer, and they're going to be walking you through an application that they've generated using some of the features that we're launching here. We're going to present this session like a play in 3 acts. So I'll do the setup, and then Bob and Daniel will come on for the main act, and then I'll come up and do the wrap-up. So if you only have attention for one act in our play, it's the main act, the one in the middle. You can tune me out for a little bit, but pay real good attention to the stuff that Geotab talks about, because it is super cool. All right, so here we go. There are a few things that we need to know, to get the demo that Geotab is going to show. There are a little bit of background knowledge. I'm assuming that most people have heard of what BigQuery is. I'm not going to dwell on this. BigQuery is Google Cloud Platform's enterprise data warehouse. It goes super fast over super big data. For more details, see the other 67 talks on BigQuery. I did want to dwell on this one, though. And so GCP has over 100 products, so there are over 100 little blue hexagons. And I don't know about you all, but I can get a little bit lost in amongst them. So I wanted to put this slide up to talk just a shade about where BigQuery sits relative to the other storage and database products. I'm not going to go through all of them, but you can see that way over here on the left side is the data warehouse. It's kind of like a relational data warehouse that can go over incredibly large volumes of data. Real good for analytics and dashboards. I think this is going to be useful to the folks watching on the video as well, to just have this one as a reference. OK, so now we'll get to the, so that's a little bit of pre-work, a little bit of homework. Now we'll get to the cool thing. So the thing that we're talking about right now, the thing we're introducing, the thing we're really launching is solving this analyst's problem, solving their use case. They want to be able to analyze and visualize geospatial data within BigQuery. Right now, it's possible, but it's not super easy. So we're going to change that. So first, a little bit of background. So what's the difference between a geometry and a geography? So when my kids draw lines on the map, they say, oh, how do we get from Seattle to LA? They just draw a line on the map, right? They're doing Euclid, although they don't know it. The shortest distance between 2 points is a straight line. That is perfectly accurate, except if the surface that you're talking about is actually curved, such as our planet here. So in this case, the shortest distance between Seattle and Stuttgart is this great circle route. However, Euclid was not wrong. If you look at that from space, you get that straight line again. So the point of this is that if you want to express geometries on the surface of the Earth, obviously you've got to take the curvature of the Earth into account. Otherwise, you get the math wrong. That's really the whole point of this. So can you properly do GIS in BigQuery using SQL? Any guesses as to what I'm OK, right. Thank you. I saw a couple chuckles in the back. So the answer is yes. And that's the capability that we're launching right now. So we are bringing geospatial data types and geospatial functions into BigQuery as first-class citizens. And that is, I mean, I know there's no fireworks going on, but that is super cool. Let's press in a little bit. So this is a 200-level talk, so we're going to get into some details. I'm not going to read all of this, but what we're launching today is native support for many categories of st_star functions. So those of you who use PostGIS will find this very, very comfortable. And I put this slide up here both as reference for later viewing and as an indication that there really is quite a wide swath of functionality that we're introducing here, right? From predicates to parsers and formatters, et cetera. Here's a list Oh, sorry. Here's a list of the data types that we're supporting. So points, line strings, polygons, polygons with voids in them, multi-polygons, and then a collection is one or any number, or any, well, collection is one, any number, or any combination of all of these above. The formats we're supporting right now are well-known text and GeoJSON. We'll be adding support for ingesting shapefiles natively really soon. Here's a list of some of the functions that we're launching right now. A couple of our favorites. We've got links to queries, so if you've got access to the slides later on, you can just come and click on this, and it'll take you to a BigQuery query where you can play with the join based on std within. But for those of you who use these kinds of functions or have used these kinds of functions in the past, this should look pretty familiar and feel pretty familiar to you. Anyway, we're super stoked about that, but that's really only half of the problem, right? Like when you write a query and you print out a geography in the table viewer portion of the BigQuery UI, like for example, there are census tracts and there are zip codes that have thousands of vertices, and so if you just print out that row, you get 1,000 lat long pairs. Like, that makes for a very poor user experience, right? Tables is not how human beings visualize or interact with geospatial data. And so we have a couple different options for folks to do viz on geodata inside of GCP. Number one is for hardcore mappers, right? You can go ahead and use Earth Engine. You can export geodata from BigQuery, import it into Earth Engine, and then use the JavaScript console, which is that middle section of tiny text right there, to create whatever map you want based on the data that you just brought in from BigQuery. So for hardcore mappers, so first off, it's a bit of a pest to have to do the export and import. But for hardcore mappers, they might find this one. They might find that a perfectly reasonable workflow. And in our alpha testing, it's borne out that way. However, how many folks here they just go ahead and use SQL? Quick show of hands. All right, so for you all, we have this use case. Hi, I'm an analyst. I like BigQuery. I just wrote a query that has a geospatial data type in the result. Would you please let me view that on a map? And so to do that, we're actually launching to alpha as well BigQuery Geophys, which is a lightweight mapping tool that you can use to go ahead and compose a query here in the window, and then you run that query, and then it calls BigQuery to run the query, populates the results here. You tell it which column you want to draw, and it drops it onto the map, and then you can do real-time styling. Now this downloads those results all into the browser's memory. So, oh, sorry, we don't need to watch the GIF go around again. It downloads the results into the browser's memory, so it's not like an infinite cache of geodata that you can draw. It's limited to about 2,000 points or polygons. However, for the case where you just want to see the result on a map, we thought this was a much better experience than, well, honestly, anything else we could think of. And I would like to point out that the engineer, Mr. Don McCurdy, who did this, is sitting right here in the front row. So thank you very much, Don. Alrighty, 2 more things you got to know before we get to the demo. Trust me, it's only 2. So BQML is one of the really big launches that we've had here for BigQuery. It was highlighted in the keynote earlier. But this fundamentally is the ability to create models, evaluate models, and predict on models all within SQL. So we've invented some new SQL verbs, and all inside the BigQuery UI. So gone are the days of needing to export data to GCS, ingest it into TensorFlow, or Cloud ML Engine, or into Spark ML, or whatever. You can do it all inside of BigQuery. So that simplifies life a lot. We're going to use that in just a second. The other thing you need, so that's one of the basic building blocks. The other piece of information you need to have before we get to the demo is who's consuming this and what's the problem. So Smart Cities is a data-driven initiative to try to alleviate some of the traffic or infrastructure congestion problems that are plaguing cities, not just in the States, but around the world. And so like growth, and this is a really significant thing, right? This is not just us spending more time in traffic as we go to and from work. Like, decreases in the ability of folks to move around cities is materially impacting accessibility to jobs, accessibility to opportunity. It creates incredibly high gradients in housing prices, which makes markets a little bit less stable. And it talks, and it speaks also to environmental sustainability and the quality of life that we have in our cities. So it's a big problem. And by applying data and analytics to it, we might be able to use our infrastructure much more efficiently. Now, the cynical among us, or at least the data cynical, and I imagine there are very few data cynics in this particular audience, given the crew here, but the data cynics might ask, like, well, you know what? Why don't we just build more? Well, Seattle, that's where I live, cannot handle a 400-lane highway. There's just not enough room. So we have to use data and analytics to do things like optimizing like real-time adaptive spotlights on streets. Rideshare is a data and analytics heavy application. My favorite one on this list, rideshare and flying cars. All right. So all of these techniques are heavily reliant on data and analytics, and so we have to produce these technologies. Google has to produce these features so that companies like Geotab can help smart cities decide how to use their infrastructure more wisely. And so we've covered a couple things. We've covered the launch, right? So BQML, BQGIS. We covered the Viz tools. We covered the background information. And with that, I will give up the stage and let the main act come on. Bob.
Thanks, Chad. Thanks, everyone. So before we get to the demo, I just want to explain a little bit about who Geotab is and what we do. So Geotab is a global leader in the telematics space. We have an open platform for fleet management. So for those of you that don't know what telematics is, it's connecting commercial vehicles and reporting where they are and other information about them. So it's kind of a nice coincidence that we're surrounded by all these cool, colorful tires here. And so we have 1.2 million vehicles, or over 1.2 million vehicles, driving around the world every single day. And that produces 3 billion rows of data each and every day that we ingest into BigQuery. An interesting thing that we do at Geotab is we have a patented data reduction algorithm, a curve-based logging algorithm, that allows us to minimize the amount of data. So those 3 billion rows, once they land in BigQuery, we can explode those out by interpolating into really, really large, usually 10-fold data sets. And I was going to come up and explain a little bit about the size of the data we have in BigQuery, but I just found out from Chad before this that the stat many of you saw this morning, the largest query ever written in terms of rows was one of our employees, so 28 trillion rows, which was awesome. So that's cool. But we also believe we have the richest data set in the telematics business. And why do I say that? Is because we're much, much more than just points on a map. Although obviously we have no lack of points on a map. This is one day of Geotab data in North America. But we collect a whole host of other information that's useful for fleet management, but also extremely useful for smart city applications. So we manufacture the device and the software, and on device, we have an accelerometer. The accelerometer measures 3-axis accelerometer movements in forward and back, so we can detect harsh braking incidents or hazardous incidents that result from hard acceleration. We can have side-to-side movements, so we can tell if people are swerving around objects, or if there's corners that people are taking too fast, and maybe they're blind corners, or you need to add a sign. And up-down allows us to monitor road conditions, so we can do things like identify potholes or bad road conditions. Another interesting thing we do is we actually reverse engineer data from the vehicle itself. And that includes a lot of things that you'd expect, fault codes, seatbelt usage, engine RPM, but it includes some really, really cool things that you wouldn't think of, like ambient air temperature and outside pressure. And we can use those things to generate hyper-local roadside weather and pressure maps. And we also get windshield wiper information. And with 1.2 million vehicles driving around, we can actually predict if it's snowing or raining just by the activity of the windshield wipers in various areas. And we can combine all of these things to generate driver behavior profiles and tell if there's areas in a city that are hazardous or that need some attention because there's accidents there. And if you want to learn some more about what we do at Geotab, we actually just published a joint case study with Google. It's a really, really good read. I'll leave it there for the folks on YouTube. And check it out, learn a little bit more about Geotab. Now, when Chad asked us to talk about some of the stuff we did with GIS, I wanted to mention and make sure we talked about this, that Geotab has been doing GIS in BigQuery for some time. So we've been a long-time BigQuery customer, and as you can imagine, most of our data has a geospatial component. So over the years, we've been developing ways to do geospatial analysis in BigQuery. And one of the coolest features of BigQuery, in my opinion, is the JavaScript UDF functionality. So we are able to use the JavaScript functionality to bin our data into geospatial buckets, like S2 cells or geohashes. So what you're seeing here on the right is a map of temperature changes, hyperlocal ones, and as I've learned in my short time here in San Francisco, the weather changes when you change streets or turn corners. And so this is really, really cool, and we can do boxes of 500 feet by 500 feet and actually aggregate and anonymize our data and show it on a map. And we can also do things like create inline functions here to do haversine distance. So we've been doing geospatial for some time, but the GIS functions accelerate this development and really, really allow us to build smart city applications on top of our already existing platform. So that map you saw before, where we could bin it into S2 cells, or we could, we could look at using geohashes. Now what we can do is we can aggregate and anonymize and pull statistics across arbitrary shapes. So it could be a GeoJSON file, it could be a shape file, and we can perform all of those cool st_star functions that Chad said right within BigQuery. So now we can do distance and intersection and contains and all of those cool things. So that map we had before, where we were looking at boxes on the Earth, was really cool. But we can also now just go out and get some open data. So I took an open data set of neighborhoods here in San Francisco, and I can use an st_contains and just find what the temperature is in every single one of these neighborhoods. And we can do this with anything that we have in our big data environment. So now we can look at which neighborhood has the most accidents or the most hazardous driving. Or we can look for hotspots of idling and make an environmental impact. Really, really cool stuff that we can do. And what makes it even more powerful for us is that every single smart city out there, or every aspiring smart city, have their data in shapefiles or GeoJSON. And they also have Geotab devices in every single one of those cities. So I'm going to talk to you guys about a real-world use case, and we've been starting to develop an application around this that builds upon our open platform that involves driving pattern and driving behavior and looking at it in front of a school in New York. So I'm sure a lot of you have driven over these things in the past. And so let's imagine for a second that you're dropping your children off at school in New York City, and you notice that, in your opinion, there's some people driving through in front of the school very, very quickly. And so you make a call into 311, and you voice your concern. You're a concerned citizen. And so what might happen today is someone would go out and install pneumatic tubes across the road and conduct a study. And they're measuring the volume of traffic that comes across those tubes and the speed that they're traveling. And they collect the data for a few weeks, they bring it back, they analyze it, and then they get back to you, the concerned citizen, with the results. And what we think is that now that we have these geospatial functions, we can spend a few minutes and do a virtual study with a virtual pneumatic tube using the new functions in BQGIS. So before we get to the demo, I'm just going to do a couple little under-the-covers things to showcase how we use some of the geospatial functions. So the first thing we wanted to do for this demo was we don't need to look at 1.2 million vehicles to figure out what the traffic looks like in front of a school in New York. So how can we filter that data? In the past, maybe we would have used a bounding box, and we would have tried to use latitude and longitude. But now, we can go to the NYC Open Data Portal, and we can pull down the data set of school zones. And we know, in this case, we're looking at the neighborhood charter school in District 6 of New York City. So let's filter by District 6 in New York City. So you can see here, we would pull our GPS records in, which would contain all of that traffic information, speed, cool stuff that we can get that you can't get from a pneumatic strip, like types of vehicles that are driving over the strip, et cetera. And we would use an st_contains. And what I thought was actually especially cool about this was the NYC Open Data Portal had the data sitting in a CSV. So there was no transformation. I just downloaded, uploaded, and ran my query. Pretty awesome.
Cool.
Now, the second thing we need to do is we need to understand which vehicles are actually crossing this fake pneumatic tube. And the way we do that is by leveraging the lag and lead operators in BigQuery. So you can imagine as you're driving your vehicle along, you're dropping GPS points on the road. And what we're doing is we're taking those GPS points that you can see in red, and we're connecting the lag point with the current point to make a line. So we're making thousands and thousands of these lines as they're dropping their GPS points. And what's important to us is which of those lines intersects with the fake tube that we've drawn on the ground. And so you can see here our subquery is looking at traffic, and so here's where we're making those lines. So we're using an st_makeLine function, and we're taking the lag point and the current point that we have sitting in BigQuery, and we're making thousands, if not millions, of these tiny little lines. And down below here, we're using the intersect function to look at which of those intersect with the line that we drew on the map. So we can get a true representative of the vehicles that are actually crossing in front of this school. So with that, I'll jump out and do a quick demo. So what you can see here is an add-in that we've made that lives within our open portal. So we have hundreds, if not thousands, of these add-ins now that are built upon our portal. We built some of those ourselves, and that's what we have here. And I've left myself a pin because there's no way in front of all of you I was going to be able to find the school that I wanted to go to. So what we have here is the neighborhood charter school that we were talking about. And if I zoom in, my complaint as a citizen of New York was that I feel like 145th Street, the traffic is just moving too quickly. So what I can do is I can come over here, and I can create this virtual pneumatic tube. And I'm going to draw it right across 145th Street. Whoops. And once I have the tube drawn, I can run the traffic study. And what we're doing is we're going out to BigQuery. Chad, you got any advice here?
That's not supposed to happen.
That's not. So what's happening now, while Chad's logging in, is we're going out to BigQuery and we're looking for all those vehicles that are crossing that line. Thanks, Chad. And we're pulling back statistics. So now, as an employee of the city or the municipality, I can get some information that I can give back to the citizen. So I can see and I know that in New York, the average speed or the speed limit in front of a school should be 15 miles an hour. So on the surface, it doesn't look too bad. If I break it down by hour of day, it looks like people are pretty well behaved. But if I look at these average speed bands over here, I can see 16% of the people are going between 25 and 30. Another 3.5 are going over 30 miles an hour. So there are actually some 20% of the people that are speeding through this area quite substantially. So there may be something to that. I also get a breakdown of the types of vehicles that we see, the average speed and the trends. And I also noticed that Saturday is a particularly bad day. People are driving much, much quicker on a Saturday. Now, of course, kids aren't in school that day, which is great, but still something to be concerned about. The other thing we did is we used the District 6 to go out and pull in information that we already calculated at Geotab for smart cities around hazardous driving areas and road impediments. So we can see here the green represents areas that are hazardous. So that's where we see a lot of harsh braking events or swerving or accidents happening on aggregate across all of our vehicles. So while in front of the school is not too bad, just down the street at the corner is pretty hazardous. And this could cause issues that back up traffic, or maybe that's a path that a lot of these students are walking to school. And in blue, we measure the road conditions, so good news in front of the school is pretty good. Over here, maybe you could use some attention. So you can see the kind of things that we can do using the GIS functions. And what's awesome about this as a developer is that it's just a select statement. There's no other work that needs to be done. And all of our data gets to stay within BigQuery, whereas in the past, we might have had to pull it out and then compare it with shapefiles. Everything right now happens right inside BigQuery. So that's it for my demo. I'm going to pass things over to Daniel, who's going to show you a much, much cooler demo combining BQGIS and BQML. Thank you.
Cool. All right, so I'm going to talk to you about, combining BQML with the BigQuery GIS functions. So for those of you who kind of missed the spotlight session earlier, which it seems like it was most of you, we kind of demoed the tool here, which I'm going to get into more details about. But essentially, on the left here is the current hazardous areas for the city of Chicago, and Bob kind of mentioned the accelerometer data that we get, and we can kind of aggregate those over time to see where there are particular problem areas where we're consistently seeing relative and kind of scale to the proportion of vehicles that are driving through that area and the volume of traffic, where there's problems and patterns of hazardous driving behavior. And on the right is actually a prediction of where these hazardous areas are expected to be based on predicted weather conditions. And it's going to be really cool. I'm going to walk you through how we actually built this demo. And all of it happened within BigQuery. As Bob mentioned, we never have to leave using the new functions. So as a data scientist, I love playing with machine learning models, obviously. But now that I get to use kind of these GIS tools as well, combined with them, we can do some pretty awesome and powerful things that were really difficult before. So just stepping back a moment, I mean, Bob kind of already mentioned this briefly, but I just want to sort of talk again about how we actually calculate these hazardous areas. So we've got our devices in all of these vehicles, and we're constantly monitoring the accelerometer. And so the types of harsh driving behavior that we're looking for are things like harsh braking, rapid acceleration, harsh cornering, relative to kind of the speed of the street where we wouldn't expect that kind of thing to be happening. And we're also going to be detecting accidents constantly as well. And we aggregate these over time, and when we look at the accelerometer events beyond a certain threshold from multiple vehicles in this area, we can start to classify it as hazardous. And we're constantly calculating these areas, every single day globally across the entire planet and storing them in BigQuery daily. And so if you're the city of Chicago, obviously you don't care about all of this global data. You're just going to want to filter out the subset of areas that are relevant to you in the city. And using these cool GIS tools, they can just upload a shapefile to us, and then we can run a simple select statement and pull out all of our data, within that red bounding box area for the city of Chicago, which is super cool and a lot easier than what I had to do before. So before, we were still doing this kind of stuff, but I would have had to do things like, cache a table that had reverse geocoded, S2 cells or geohashes, look for, within certain bounds, that kind of thing. But now it's a one-liner, which is fantastic. But what I think is even cooler than kind of aggregating this information over time is what we can do in terms of predicting the future. So, cities are obviously really interested in what's happening right now in terms of hazardous areas, and they're going to want to know the severity of those things and how to prioritize road work and maybe improve signage, add things like, speed bumps and things like that in the road. But what's more important is actually being proactive and addressing, safety concerns before they actually start to hurt people, especially in front of things like schools. And so I thought a really cool use case would be use some of the public data that's already available in BigQuery to kind of build a model around weather and see how, if it's going to be a particularly snowy day or if it's going to be a really rainy day or we're losing visibility, how is that going to impact traffic around the city? And the city can maybe say, okay, we're going to have a particularly harsh winter with a lot more traffic volume than we're used to. What's going to happen and what areas do I need to address before that becomes a problem? So stepping back a little bit first, I need to actually do kind of a sanity check to see if that's something that's even going to be possible. So I took the last 2 years of our hazardous driving area for the city of Chicago, kind of started to parse it out by weather conditions and looked, was there any measurable impact in our data from weather on kind of the relative severity of hazardous driving across the city. And so I used a variety of the GIS functions, but essentially here the ST snap to grid functionality to bin things across the city and then calculate the average severity score and correlate it with weather and produce some of these cool maps that you see here on the screen. And so you're going to notice they're a little bit jiggled around there. So after doing the aggregation with the ST snap to grid functionality, I just shifted them around by the average latitude and longitude for each of those sections where we're historically observing hazardous driving areas so that we know, we can tell the city specifically where the problem is on the road so they can go and address that. After producing these maps, my first thought was, cool, this is awesome. I can immediately see a big difference between the winter and the summer and these particular days here. So there's probably something that I can do with a model that I'm going to be building in BigQuery to start to predict these things before they happen and see what kind of the relationships are mathematically between weather and the hazardous driving areas. One of the cool things that was sort of non-obvious to me that jumped out from this was on the left you see, obviously there's a lot more hazardous driving and hazardous areas in the winter than the summer, but the highways actually are proportionally less dangerous than the neighborhoods of the city, which was a little bit counterintuitive to me. So you're possibly more likely to get into an accident going to or from the highway than actually driving on the highway, just because of the amount of harsh driving relative to the volume of traffic that's going through that area. So great, this seems viable, and historicals data is really interesting, but how can we actually use that to start to make some predictions about the future? So we're going to dive in a little bit under the hood into how we actually made the Spotlight session happen. So yeah, it's really easy to pull in all of these things. We can aggregate, with some simple ST functions, the hazardous areas for the city over the past few weeks or the past few months or whatever particular historical period they might be interested in, maybe filter that by severity score and give them an idea where they might want to prioritize their road work. And for a city, this is super cool, but if I'm a city planner, I want to address things, again, proactively before they happen. So what about tomorrow? What about tomorrow if it's snowing? What about tomorrow if it's snowing and there's low visibility? There's all sorts of conditions that could happen tomorrow, and maybe you could go back and find an exact historical correlate for what happened with that, but that doesn't take into account kind of your projected traffic volumes. Your speeds on these streets change over time. The weather patterns change over time. A lot of things are changing. And so if you don't understand the relationships between those, I can't just look at historical data. I need to be able to predict the future. And so that's what we're going to do using just BQML, and we never have to leave BigQuery to do any of this, which is the coolest part. And so we can join the data that we have, our historical driving data, with all of the public data I mentioned that BigQuery already has available for daily weather. They have this going back decades for thousands of weather stations across North America, and there's several of them that happen to be around Chicago. So I can interpolate between all of those and get, roughly for that day, things like the average temperature broken down by that grid that we did with ST snap to grid functionality. I can get the max temperature, the min temperature, the visibility for that day, the total amount of precipitation, whether it was foggy, whether there was funnel cloud formation for tornadoes, all of this cool things. And then I can use all of these new BQML tools, which have been announced several times today, to start to train on this data. And so in just a few lines of code that you see here, I'm able to train a model that's going to be doing all of this prediction for me. So a few lines of code, really simple, really powerful. So in reality, I actually created over 300 features for this model, which are various kind of transformed versions of weather inputs, combinations, things like temperature scaled by visibility, and functional transformations and things like that. Unfortunately, that wouldn't fit on the slide, and Chad wouldn't let me do it anyway. So this is the simplified version of that. So if you just sort of use your imagination, and the temperature, visibility, snow, rain, and fog here are actually reflective of much more complex features. But there's a whole lot of things going on here that you see on the slide, and there's actually even more going on behind the scenes, which I'm also going to talk about, and which I think is the kind of really key part of what makes BQML so powerful, and what was going to really make it powerful for analysts as well, who maybe don't have as much data science background. And so in the first line, we're just telling BigQuery to create a new model, simple enough. And then we can provide some options for BigQuery and how it's going to actually fit this model and what kind of hyperparameters we want it to use to do that. But the only actual required things here are the model type and the labels that I want to predict. We can specify a whole lot of other things too, though, such as like the minimum relative progress, the learning rate that I want it to use, if I wanted to do regularization, what type of regularization, the maximum number of training iterations, the learning rate strategy, all of these things I can tell BigQuery to do, but I don't have to because BigQuery is going to handle all of that for me and do this kind of hyperparameter optimization for me. BigQuery is automatically going to create a train test split of my data. I can manually specify that if I want to, but again, I don't have to. It's going to do the train test split for me. It's going to set an initial learning rate, and it's going to adjust it during gradient descent algorithmically. I don't have to worry about that either. One of the coolest things, especially when you have over 300 features, is that it's going to center and normalize all of my features to zero mean and unit standard deviation without me having to do any of that. It saves me a heck of a lot of typing. It's also going to automatically one-hot encode all of my categorical variables. I don't have to do that either. And I think there's going to be some additional functionality soon that you can automatically bucketize things as well, which is fantastic. And because it's automatically creating this train test split for me, it's actually keeping track of the loss by iteration, so I can immediately go as soon as this model's been trained and quickly check for overfitting, which again is fantastic. And I don't have to code any of that behind the scenes. I can do this with just a few lines of code, which is fantastic. And just to reiterate, all of this is happening inside BigQuery. I still haven't even left the same browser tab that I opened to begin with, which is fantastic. So this particular model that I'm going to actually show you the demo for, I trained on about 600,000 training examples. And the query for training the model only took about 15 minutes. And if you remember, I mentioned I've got over 300 features, so that's over 180 million data points used for training that BigQuery is able to parse through and fit a model to in under 15 minutes, which is fantastic, using nothing but SQL code. So, okay, I'm going to take a breath for a moment. There's a lot of things happening in that slide, but okay, you're the analyst, you've set up this model, you've got your coffee, you come and sit down, and wow, okay, the model's already trained. Fantastic, let's start making predictions, but not quite. Is it actually any good? Luckily, this functionality is already built into BigQuery for us. So again, super simple, just a few lines of code that you can kind of see here, and they're rather self-explanatory on the slide. But I still haven't left the same tab. I can do all of my evaluation off of tables that BigQuery's already created when I trained this model. We've already got what we need for a basic overfitting check because it did that train test split for me and created that loss table. But we can also easily use this evaluate statement to pull out some summary statistics, like the mean squared error of the model, the R squared scored, the percentage of explained variance. And I can see if we're on the mark, if we need to maybe go back to our data cleaning step, our feature generation or selection stage, and train again. Luckily for us, I've already done all this dirty work, and we can just skip right ahead to making some cool predictions about where the dangerous areas are going to be. So after the last couple slides, this is probably going to sound familiar, but we can do all of our predictions with just a few lines of code, and I still haven't left the same open browser tab. It's really, really cool. So the syntax here is almost identical to the ml.evaluate statement that we were running earlier. We basically just pass in the model that we've already created and trained, and hopefully as a diligent data scientist or analyst, you've already gone through and done the appropriate evaluation to make sure that your model's actually predicting something and explaining an appropriate amount of variance that you can use it for something. And so I've done that. And so what is this actually going to look like, and how could a city use this to actually do something actionable with this data? And so I'm going to kind of jump into the demo and show you what that app actually looks like. So this was from the screenshot that I showed you at the beginning of this section. On the left here, just to reiterate, was the current hazardous driving areas in Chicago. This is real data, by the way, all of this. So this is the current hazardous driving areas in the city of Chicago that we measured and aggregated over the last couple of weeks. So you can see that particular areas of the city, specifically in the south of Chicago, are kind of dangerous to be driving around right now. And a city might want to zoom in on these areas and figure out exactly where these problems are and address them. But as I'm trying to reiterate, it's better to be proactive than reactive in addressing these kinds of concerns. And so let's say that it's coming up to the fall and it's going to be a particularly cold, snowy day, and let's drop the temperature down a little bit. So let's say it's going to be, I don't know, maybe 31 degrees on a particular day, and there's a lot of snow, so maybe I'll drop down the visibility a little bit. We'll say that it's snowing, and let's say it's the holiday season, and people are really excited to get out and do their shopping, and more people are on the road than usual. Let's say maybe traffic volume is 20% higher than it usually is. So let's run the predictive analysis and see what the model thinks is going to be the dangerous areas in the city of Chicago for that particularly snowy, cold day with a lot of traffic. Boom, so the map looks really different. So some of the areas that were hazardous before are still hazardous, so great. I mean, the city definitely knows now to prioritize those areas. But what's really cool is that areas in kind of the top left here and in the north of the city, which weren't dangerous before, are actually predicted to get quite hazardous on this day. So if a city is just basing, their actions for fixing, road conditions on the historical data, they're going to miss a lot of these areas that can become quite dangerous with different weather conditions. And so if we actually zoom in on a particular area here, that I found before when looking through the data, one of these predicted dangerous areas is right next to a school. So you're looking at the historical data, the city's not going to know that there's this dangerous problem right in front of a school. And so with this cool tool, we can actually use our little Google person and jump down here and see what's happening. So if we drop down a little bit ahead of where this hazardous area is happening and look around, we can see the school there, which is cool. And actually, if you notice up in the distance, there's a student crosswalk up there, which is great. That's good signage for safe areas. But if we look around here, we actually see that the bike racks are way down here next to this alleyway. So the students are probably coming in and out of this alleyway. And if we step over here a little bit, we notice there's no stop signs and no signage on this alleyway either. There's no speed bumps or nothing. So the hazardous area is happening right before this alleyway here. And the nearest signage is several hundred feet up the road near this crossing sign. But it looks like most of the students are actually crossing here. So the city might want to come out and maybe think about putting some speed humps here or some additional signage or maybe some mirrors around these corners and addressing this problem that wouldn't otherwise be obvious based on their current historical data. So hopefully you found that interesting. I found it super cool to play with these new tools and kind of build these models out and never having to leave BigQuery. And we're able to kind of train this model on this data. The actual model trains in 15 minutes, but even going through all of the feature generation and the ability to quickly iterate through, training and evaluating within the BigQuery environment enabled me to put this model together in a matter of weeks, which is really quick turnaround for something this powerful. So with that, I'm going to turn it over back to Chad. Thank you.
All right, so that was exceptionally cool, and I did want to touch on the timing. So we reached out. We've been working together for a while, but we reached out to you to talk about hey, I think there's good material for a demo for next year, and that was really only 2 months ago. And so getting spun up on the GIS features, getting spun up on BQML, crafting the thing, and then producing that awesome demo. That's not just a demo that's going to be fun for the city planners in Chicago are going to love that. Anyway, so I just wanted to give it up for Geotab, both the speakers here and the folks back at the home office who worked on that. You guys did a fantastic job. Thank you. Alrighty, so this is the wrap up, right? This is the third act of our 3-act play here, and I just wanted to review a little bit. We're not going to go through everything, but we talked about what the launches were. We talked about how Geotab is able to craft that, not just into a cool demo, but into a product that they can then, these are new product lines that Geotab and other companies that want to leverage this can then generate for smart city applications, or what's also getting me excited about this, right? the third act isn't the end, right? There's an encore, right? There are ring studies for retail, ride-sharing applications, IoT, media studying DMAs and MSAs. Like using these new features inside of BigQuery actually opens BigQuery up to enormous new volumes of work, which is what we're all about, right? We want to make our tool useful to as many people as possible in as many different domains as possible. So that actually brings me to a final analogy here. There is quite a lot of geospatial data that's already resident in BigQuery, right? Bob was talking that Geotab has been doing GIS work in BigQuery for quite a while. But there are lots of columns in BigQuery tables that have latitude or longitude as the column header. So the data, in some respects, is already there. Certainly, the data is in other data stores that folks haven't brought to BigQuery because we didn't support latitudes and longitudes. And this is the analogy with Street View. So what was it, back about 2006, 2007, Google went through the world's streets and took pictures of facades, street pictures like this, and just logged where they were in the world. We made the Street View home database. What we weren't able to do at the time that we collected that data was in detail look into those pictures and extract information like where are the traffic signs, what are the street numbers, what are the retail establishments that are at that location. We couldn't do that. Since then, we've developed the ML technology to look into these images and pull that information out. And we've even productized those as Cloud ML APIs. And that's generated an enormous opportunity for us and for our customers in that we can now look into these data sets and provide metadata on like these are the stores, these are the establishments that are at this location. And so we've actually been able to generate a lot more value off of this trove of images that we collected a decade ago. And that's the state that I think we're in right now in terms of geospatial data in BigQuery. People have been collecting geospatial data, people have even been storing it in BigQuery, but they've lacked the tools to really go in and dig out cool stuff like what Bob and Daniel showed. So I'm very, very, very excited about this, and I think we're at an inflection point for this type of work in BigQuery.